Section 21.4 is about exponential functions or exponential graphs. I really like these. I like to call these the taking off graphs. Just work with me on this one. 5 to the power of 1 is 5. 5 to the power of 2 is 5 times 5, 25. 5 to the power of 3 is 5 times 5 times 5, 125. 5 to the power of 4 is 5 times 5 times 5 times 5, which is 225s, which is 625. We are really taking off. After a power of 4, it's really moving. So hence, check out the shape here. This is page 318, the very first question, claims to be A star. It's dead easy though. So here we have the graph of y equals 5 to the power of x, and as the power goes up to 2, look straight away, power of 1, 5, power of 2, of course 5 squared is 25, it makes sense. 5 to the power of 3 will be way off the scale in terms of the scale of this graph anyway, but look at it, as the power increases, the final value for the y value increases drastically, quickly, rapidly. So that's the sort of shape you get. And of course you can get negative powers, and you may recall that from previous topics that a negative power gives you like a fractional answer. So you know the y values will be tiny little fractions which you can barely plot, and there they are, just there in a negative side of x here. Right, so use your graph to estimate the value of 5 to the power of a half. Well, the powers are down here, so I've got to take my little line function, maybe do this. So 5 to the power of a half. So, oh sorry, I'm up here. 5 to the power of a half. So here's a power. Hit this. Turn left. Not brilliant, but that's the best I can do. So 5 to the power of a half is going to be roughly 2.1 maybe, I don't know. So it's gone above 2 slightly. I know it can't be 2 because 2 times 2 is 4. It's not quite there. So I'm going to go for 2.1. Just write it down. So that equals 2.1 approximately. And then we're going to do 5 to the power of 1.5, 1.5. That's here. This will be easier to read, I think. Bam, hit it there, turn left. Well, it's conveniently landed on 12, so I'm going to run with 12. Again, I should have shown arrows. Always shows the examiner what your brain's doing. So 5 to the power of 1.5 is approximately 12. Now we're working the other way. Use your graph to solve the following equations. 5 to the power of something is 1. Well, I know the answer straight away is 0, because any number to the power of 0 is 1. Let's just prove it. So 5 to the power of something is 1. Well, there's the 1 right there. We're reading straight down to the onto the x-axis, and it's pointing straight to 0. Yeah, we know that anyway. Now what about this one? So 5 to the power of something is 10. Let's just read over in red. So what's the power then? So the y value is 10, so let's try and hit it right here, get them on here with the other little blue ones. Oh, not bad, not bad, not bad. So I've got, I make that about, in fact I do make it 2.4, 1, 2, 3, 4, yeah, why not, leave it in red, 2.4, so 5 to the power of 2.4 from reading from my graph is approximately 10, that's what that's saying there. There's your other arrow. And the next one, 5 to the power of what makes 20? Well, let's go up to 20 then, using the line facility. Hit the line, come straight down, about there. So I've gone across, hit my curve, and come down, and I make that 1 square before the 2, I think. Or is it 2 squares? Hard to tell. I'm going for 2 squares, so I'm going to make that 1.8. It's best I can. It may even be 1.9 between 2 squares. It's not overly accurate. 1.8, go on, leave it like that. Can't argue about it. So 5 to the power of 1.8 is approximately 20. That's what we're chatting about here. And that's question 1 done, reading off a curve. Question 2 is longer. They actually want us to draw a graph, but again, as usual in this topic, it takes so long that I've prepared the graphs anyway. It says, question 2, copy and complete the table values for the exponential function, you know, the exponential graph y equals 3 to the power of something, and we go from -3 to 2. So here we go. So 3 to the power of -2 is 0.1, 3 to the power of -1 is 0.3 recurring. So let me just show you how I did that one, for example. Well, I've got y equals 3 to the power of -1. There's the -1 right there. Remember, the x is the power, and you should remember from previous topics that a negative power like that means 3 to the power of minus 1 can be written as 1 over 3 to the power of 1, and 1 over 3 is exactly 0.3 recurring, so 0.33, which is sort of plottable, is good enough. Next one, 3 to the power of 0, any number to the power of 0 is 1, so that's the one, that one, and that's what I did with this, with all the others as well. Well, they did all the others, I just did the last one. We know that 3 squared is 9, so that's not very difficult, is it? So 3 to the power of 2 is 9, dead easy, etc, etc. Thankfully there's only 3 to do. Now draw the graph of y equals 3 to the power of x. Look at it take off, isn't that lovely? Look at that beautiful curve. I didn't draw it brilliantly, but look at it, it's taking off already. And there's your 3 squared is 9, there's your 3 to the power of 1 is 3, your 3 to the power of nothing is 1. So it all makes sense mathematically, and the shape makes sense as well. Y equals 3 to the power of x. Stunning little graph. Now we're going to read off it. Use your graph to estimate the value of 3 to the power of 2. So y equals 3 to the power of 1.2. So 1.2. Line facility 1.2 is about here. It's not brilliant. It's really hard to get it. Oh, in between goes. Let's just plant it there and have it done. Right. That's what I'm going for. Oops. Better? Yeah. I'm happy with that. So 1.2. Read up. What is 3 to the power of 1.2 when the x value is 1.2? Answer, I'll make it 3.5. Why not? So y equals 3.5. Again, y equals 0. Y equals 3 to the power of 0.3. So let's just read off where x equals 0.3 now. 0.3 to get this facility going, 0.5 to go 2 squares back, about here on my graph. Close enough, eh? Close enough. Turn left, show the examiner what the brain is doing. I went up and I turn left. I've got an answer of 1.5. That's quite clear, isn't it? So 1.5. Love it. Now this time we're going to go the other way. So 3 to the power of something is 4. So in other words, y equals 4. So let's just read off where y equals 4. We'll work in black, I think, so it can stand out differently. So when y equals 4, let's work out what power of 3 that would be. So I'm going across and down again. This ain't going to be perfect. These are going to be rough things. I went right, then I went down, and that's about 1.3. Write it into my answers. So the power is 1.3. Next one, y equals 3 to the power of x and y equals 2. So read along y equals 2. Y equals 2 is just here. Hit my curve, come down. Again, if the curve is ever so slightly out because a human is drawing it, that me being bad, rather than a machine, then the answers will be slightly out as well. So when y equals 2, the power is going to be 0.6. That's 0.5, 0.6, 0.7. Yeah, I think that's right. So we've got a value of x equal to 0.6. And the last one, y equals 3 to the power of x. Of course, that's the graph. And y equals 0.5. Let's try and read over for 0.5, which is here, isn't it? And we've gone into negative territory, not that that matters. So that's the line y equals 0.5, and there's no point going over this side. There's nothing here but a bit of blue carpet. And then we read down like that and get the best answer we can with the graph that I've just drawn. So I turned left, and then I came down here, and there it is. So that looks like I'm going to go with minus 0.8 on that one. All right. So we have x equals minus 0.8. Now hopefully I've got a chance to do the next one as well. So what have we done? We've plotted a fancy exponential function. We had to calculate 3 coordinates, plot them, and then read off it. That's all we've done. Okay? Hopefully there's time to do the next question. Yep, I'm going to go for it, but I'm not going to do all that it says because it's too long and too boring. But I will make a big issue of it. Go thicker. Right, Claire invests £5,000 in the account, paying 2.5% per annum, so it's quite realistic. The interest is added at the end of each year. In other words, this is compound interest. It is compound interest. Let's just write it again. what's this got to do with exponential functions? We're going to see in a minute. So this compound interest, right, you don't take your money out, just add a bit on every time, each year, an extra 2.5% here and there. Write down an equation for V in terms of X, where V is the value of her investment. That means her original £5,000 plus her accrued interest, and X is the number of years it is invested. Alright, so let's look very carefully at this. The value of my investment is going to be my original £5,000 multiplied by 102.5%. That's 2.5%. And so I've got 102.5%. And I'm going to leave it in there for X years. Alright, X is the number of years. And there is my equation. And what I've got essentially is a graph not with Y and X, but with V and X, because V stands for value. But it's the same thing. They could easily have left X as X and V as Y. It doesn't matter. But it's an exponential function. That's why it's in this topic. So this is the equation. If I'm going to leave it for 6 years in there and not touch it, I'm going to earn 5,000 times 1.025 to the power of 6. And that's all I have to do. And then it says draw a graph of the equation for values from 0 to 20. In other words, leave it there for 20 years and see how much interest you get year on year on year on year. If you don't touch it for 20 years, well, you're still going to get an exponential graph, aren't you? And it's probably going to look something like this. Let's do a rough sketch. So, I don't know, that's zero right there, something like that perhaps. So that's going to be 0 years up to say 20. That's all this is, and that's going to be the X's, the number of years, and that's going to be the V, the value, and that's going to be in pounds. And all you do is just read off the graph. Alright? Now, I reckon the 0 should be on 5,000 anyway, so that's going to be 5,000. So clearly after 0 years, you still have your original 5,000 right there, and then we just go up in, I don't know, whatever it's going to go up in. Doesn't matter. I'm not going to plot it. You can calculate it if you want to do it, but I'm not doing it. It's not necessary. Now use your graph to estimate the value of the investment after 12 years. So what have you got to do? You've got to come over here and go, I don't know, 12 years, bang, bang. Alright, so this is like 12 there, and there's your first X value. And after 17 years, so that'll be up here, say, again, very, very rough, that's all it is. And that's my 17s, and that's my other value after 17 years of investment. I'm going to calculate it, because if X equals the 12 and X equals the 17, these become the power in that equation. So I'm going to calculate it, but at least I've shown you on a rough sketch how to read it off a graph. I'm trying to save time here. It's not necessary to draw a graph for that. So let me just calculate it. So go back to yellow then. So C1, not doing that. That's that down there. I'm going to go the value of my investment, not reading off a graph but calculating it. Remember, I've got a calculator. It'll be 5,000 times 1.025 to the power of 12 years. Compound interest with a calculator is a lot of fun because it's done with a calculator. So 5,000 times 1.025, remember 0.025 is 2.5%, and hit the power button, that little hat thing, 12. I don't know if you can see that, can you? Well, that's what I've got. So it's power of 12, and this investment's going to be worth, from my calculator, £6,724.44p. And that's it. That's what it's worth after 12 years. And now we're going to go after 17 years. Here I go. So £5,000, the original capital investment, times 1.025 to the power of 17 years. Same thing, just put the numbers in. 5,000 times 1.025 powered up to 17 equals, leave it there for 17 years, you would get £7,608 spot 09. It doesn't say go to the nearest pound, so I'm going to go to the nearest penny. So it's 9 pence. There you go. 7,608 squids and 9 pence. So Let's assume you don't need your money for 17 whole years, but you know, who doesn't? I mean, we're not all millionaires, are we? So that's that. So what do we got then? Exponential graphs. They've got a lovely funky shape that takes off really quickly, and this is a lovely compound interest question whereby you can plot an interesting graph. If you had one of these in the exam, I mean, count on it. What happened is they'll give you a table of values, and you've got to work out a couple of the y ones, you know, as is usual for any graph question. You get the shape and then just read off it, and that's supposed to be A star. Well, that's a little bit easy for A star, I think. And so that is it in a nutshell. That's exponential functions, just done in one video. That was easy. Let's just go back. What we got? Yep, y equals 3 to the power of x, and that's the working out. And that's the starter question, y equals 5 to the power of x. One video. Might be a bit long, but you know, take your time with it, you'll be fine.